In discussion diffraction, concept that naturally arises is one of resolution. Now, what do I mean by resolution? Imagine that we've got a slit or an opening, and we got a screen over here, and we got a light source here, light shining, light source here, light shining. And so the light shining through here, as long as this angle is very small, then this is practically normal to the plane. And so what happens is this projection image here, so the bright spot would be right here. This one projection image this way, bright spot is right there. So the narrower the opening, the more the light spreads out. The wider the opening, the less the light spreads out. Well, at some point, you realize that these two bright spots begin to overlap, and it looks like one big bright spot, and then you can't tell that you had two sources of light anymore. Now it's like just one big source. And so this is the idea of resolution. And so the idea is, how do you know what's the minimum spacing that you can have in order to maintain resolution, to separate these two things out? And so one possible solution to this was actually proposed by Lord Rayleigh. And that was that if the two bright spots are sufficiently separated, then you can easily tell. But if they're too close together, it all merges. When you add all the light together, it merges together to make one large spot. And so the Rayleigh Criterion, what he came up with was that the minimum separation in which you can just barely tell that you got two things, and that it's slightly dimmer between the two. It might not be dark between the two, so you might not get clear separation, but you can barely tell that you've got two sources. The Rayleigh Criterion occurs when the peak of one lines up with the first minimum of the other. And so we would say that the minimum resolution distance would be, now remember, the peak occurs for resolution here, okay? We know that the peak occurs when A sine theta equals lambda. So in other words, sine theta equals lambda over A. And so this would define the smallest possible angle that you could then resolve. And so then you'd be able to figure out, well, how close these two things be together and still be able to resolve them. Okay. And so we can do a couple of examples here. One possible example here would be that you had, light source here and a light source here, and then we've got a slit right here, we've got a screen over here. So again, just analogous to how I started this, that I want to know what's the angle separation here if the wavelength of light is 500 nanometers, and this separation right here, A, let's say that A is 1.41 micrometers. Okay, so the sine theta minimum occurs at lambda over A. So this is also your resolution limit. So this is going to be the resolution limit. And so we would say that theta equals the inverse sine of lambda over A. And so this is going to be equal to the inverse sine of 500 nanometers. And it was like 1.41 micrometers, so that's 1410 nanometers. And so that would be, we won't divide that out. .8 degrees. Well, gosh, that's pretty pitiful. 20.8 degrees. Well, that means anything that's closer than 20 degrees apart, you'll never be able to tell you actually get two different sources there. And so this is what happens when the size of your aperture is close to the size of the wavelength. Well, try another example. Now let's say that we have an aperture here, and the aperture size is 1 millimeter. And then we have two light sources over here shining through. Okay, and so I want to separate them. So now sine theta, okay, we're still going to say 500 nanometers wavelength, okay, is lambda over A. So theta equals the inverse sine lambda over A. So inverse sine of 500 nanometers. 500 nanometers, 500 times 10 to the minus 9 meters. 1 millimeter, 1 times 10 to the minus 3 meters. And so now you just divide this out, and notice that we have to be careful with our units. If we're not careful with the units, then this is not going to work out for us. And so we end up now with 0.0029 degrees. So now we went from like 20 degrees resolution to now a fraction of a degree resolution. In fact, when you're talking about a fraction of a degree like that, then that gets you into the idea of arc minutes or arc seconds. So in this case, that would turn out to be an angle of 10.3 arc seconds. Remember, there's 3,600 arc seconds in 1 degree.